Hi, welcome back. In the first part, we introduced the family of numbers, how they grow from the very natural, the positive integer numbers to all the way to the two-dimensional complex numbers, right? So the complex plane right now is two-dimensional, and some of you may ask the question, will they grow into three-dimensional? Maybe in the future. I don't know. And this point, although there are vectors, three-dimensional or higher dimensional vectors, they are totally different from the number space. But so far, I have been aware of any the complex space, three-dimensional complex space rather than the two-dimensional complex plane. Okay, so let's stay with the two-dimensional only. Since the two-dimensional, we need kind of a pair of numbers to represent the each complex number on or each point on the complex plane. Right? There are two different ways. So let's see if I have a complex number c. I have a complex number c. Let's see, this is the complex number, correspond to complex number c. This is the real axis, this is the imaginary axis. And c is equal a plus jb. So I have two numbers, a and b, but also I have a j. J is the square root of -1, or the j squared is equal to 1. Okay? So in this case, this naturally we call this rectangular form. Is this in this so the a corresponds on the real axis. A is called the real part, and the b is called imaginary part. Imaginary part. And both a and b are real numbers. So we use two real numbers, a pair, to represent the single complex number, to represent a single point on the complex plane. So both a and b are real numbers. So this is one way to represent this number. Let's see, alternatively, I could do this. So in this case, I don't have the real part, imaginary part. Instead, I see how far this C point is away from the origin. What's the distance between, let's call that distance as R, right? And if we draw a line, what the angle between this line, if we draw a line from C point to the origin, and how far this line is away from the positive real axis, so that we call the theta. So in this case, we represent the C as C is equal E to J theta. R times E to J theta. R is called the modulus or absolute value, of C, of this complex. Basically, how far was the distance between C point, so that's a positive real number, always. And the theta is the argument, or sometimes we just call it angle. And this angle, let's see, we go counterclockwise. So this angle, we go this way as a positive number, we go clockwise as negative numbers. So the phase angle will be negative, right? So these are two different ways of representing the same number, the same number. Let's see. I may have a number. Let's say I have a C is equal 3 plus 4j. Okay, so in this case, the real part would be 3 and the imaginary part would be 4. In that case, the A here would be 3, B would be 4. So if you have another number, let's see if you have, let's call this a C2, C sub 2, you have the distance is 10, the phase angle maybe E2J 45 degrees, or you use the reading, that's also fine. So in that case, J pi over 4. Okay, so in that case, the theta would be 4, right? So the theta would be 4. That means the line between the point C to the origin and the real axis, that's the positive angle of pi over 4 or reading or 45 degrees. And the absolute value is 10, right? So both ways we can uniquely define a point on this complex plane. Let's look at another aspect, how we do the transformation. Let's do a quick one from the polar to a rectangular. This is the easy one. So let's see if you know the R. So if the C is given R plus times E2J theta, R times E2J theta, and to find A and B. And there's really no need to memorize any of these things. So this, if you think about the figure, this is really naturally there, right? By the way, the notes to this lecture will be posted. I would put a link to the Google Share Drive, and you can check the notes. The notes basically is covering what we are talking about here, and so the theta is given also, and we're trying to find. Let me see if I can change the color. Sometimes I can. Okay, so let's see. We're trying to find A and B. Okay, so based on your so what this A and B is, right? So based on the based on your geometry, right? So this is quite straightforward. So the A would be equal to R. So this arm here, R times cosine theta, right? B is equal R times sine theta. No matter where which quadrant the C is sitting, and so I don't use the color. So well, regardless where the quadrant is, which quadrant the this complex number is in, and this is always correct. Okay, so if we know the rectangular form, we get the polar form is slightly more complicated. So we will start another part of the video to cover that. I'll see you in a moment.